We are doing chapter 5. This is part 1. I'll uh, do them in two parts, see if I can actually fit them all in one video. Okay, so in data storages, or in data storage, we use bits and patterns. And these bits and patterns have their own definitions. A bit is a binary number or binary digit, which is either a 0 or 1. And a bit pattern or bit patterns used to present information, right? So bits are binary digits, and you know what binary digits are, right? They're either zeros or ones, right? These are binary digits, and this information that is presented by bit patterns, it can either be like a number, which of course we're going to be dealing with numbers in data storages, right? And then text characters. It can be sound, it can be images, all these things. All these things, all right, etc. etc. Yeah. Now, uh, when you come to representing text, all right, you represent text in three codes. I don't know what to call them, right? In which the first one is the ASCII, the ASCII, which is 7-bit. Then we have the ISO, which is 8-bit, which is an 8-bit extend to the ASCII. And then we have a Unicode, which is a 16-bit representation. All right. So now let's write it down. Now, when you represent text, each character is assigned a unique bit pattern. All right. For example, let's say we want to represent uh, the word car, or whatsoever word that you can think of, right? Now, uh, uppercase values differ from lowercase values. All right. Let's say in uppercase A, right? In uppercase A has a bit pattern of how many zeros was that? Two, I don't know, but it was something like, I think it's six, three, four, five, six, one. All right. This is a bit pattern for zero. I mean for A. All right. Now, I mean it's, capital letter A actually. Now for small letter A, it's still the same pattern, but it's 0, 1, 1. Right? It differs here. Then here it's 1, 2, 3, 4, 5. Then like that. All right, something like that. This is like the bit representation or the bit pattern for a character. Now let's say we want to present the word car. It's going to take, well, I mean, I did say the character is assigned a unique bit pattern, so yeah, I did see a, then all right, so that's that. And I did mention again that we have the ASCII, right, which is 7-bit representation. I mean, it's 7 bits to represent English text symbols. And then after the ASCII, we have something called the ISO. And the ISO is just an 8-bit uh, extension to the 7-bit. And the 7-bit, we know it's the ASCII, right? And it's designed to accommodate a major language. Each 8-bit extension is designed to accommodate a major language. Then the last extension, I don't think I should call them extensions anyways, is called a Unicode. Now, a Unicode is a 16-bit representation, or a 16-bit to represent major symbols in worldwide languages. That's a Unicode. And then we have the binary system. Instead of writing the words in full, like binary, I'll just use BIN. Instead of decimal, I'll use DEC, and octal, those things, OCT. All right. Now we go to the binary system. Now, a binary system, or the binary system is it as itself, is based on basis of two. Oh no, not basis, powers of two, because it's already on powers of two. For example, 2 to the power 1, 2 to the power 0, those things. It's based on these powers. Okay. And before I forget, this is called a power, all right? And whatsoever is in here is called an exponent. S itself is called a power. So this is a power of 2. Don't confuse powers with exponents. Now, let's compare the binary system with the base system. I mean, with the, what do you call it? The decimal system, all right? Let's compare base 10 with base 2, all right? Now, in base 10, we have like random numbers. I can just think of a random number, 147. That's going to be that. This is called a representation. This is a representation of this binary digit. All right. Now, this number right here is denoted by a 1, right? And then this one is a 10. When they say round off to the nearest 10th, they are talking about this number, right? And then when they say round off to the nearest 100, they are talking about this number. All right. So in base 10, we know that the first number on our right is our 10. It's our 1, then followed by a 10 going to the left, and then followed by 100 going to the left, and then 1,000, a million, and so on. All right. Those things. Now in base 2, we have this number, 1010. Yeah. Now this is the representation again. Okay. And then when you denote these numbers, you denote them in powers of 2. This one is in powers of 10. This one is in powers of 2. All right. So the first one, 2 to the power 0, is just 1. All right. And then 2 to the power 1, it's 2. Then 2 to the power 3 is 4. And then 2 to the power 4 is 8. I nearly wrote 16. This is how the base 2 representation differs from the base 10 representation. All right. Here, 10 to the power 0 is 1. 10 to the power 1 is 10. 10 to the power 2 is 100. You know, those things. Yeah. Now, let me show you how to convert a binary number to a decimal number, and a decimal back to a binary. All right. Now let's start by binary to decimal. I'm going to use the same number. All right. 1010. Let's start with that. Binary to decimal and back. Okay, let's start with that 1010, right? 1010, which I can tell that it's a 10 from by just looking at it. Now when you multiply these numbers, you first count from here, right? From the further right. 1, 2, 3, 4. Okay. Now you need to have an n. An exponent of n minus 1. All right, your highest exponent is equal to n minus 1. And then we have 4. So 4 minus 1 is going to be 3. So our highest power is going to be 2 to the third. All right. Now we start writing these numbers from this side, from left to right. Let's go 1 times 2 to the power highest exponent, 3. Then we add. Here we have a 0. And then we minus 1 from this 3. It's going to be 2 to the 2 plus 1 times 2 to the 1 plus 0 times 2 to the 0. All right. Now, how much is this? This is going to be 8. This is going to be 0. That's going to be 2. And that's going to be 0. Now, 8 plus 2 equals to 10. This is how you calculate, how you convert from binary to decimal. All right. Now, let's do another example. Well, the last example. The other ones, you'll try them out. We have 1, 0, 1, 1. We need to convert it to decimals. All right. You do the same thing, n minus 1, blah, blah, blah. So the highest is going to be 3. So it's 1 times 2 to the 3 plus 0 times 2 to the 2 plus 0 times 2 to the 1 plus 1. Oh, it's 1. It's not 0. My mistake. To the 1 plus 1 times 2 to the 0. Now, by my assumption, this is going to be 11. Now, let's see. We have 8 plus 0 plus 2 plus 1. Yes, it's 11. Now, let's move 11 back to binary. Okay, I'm moving these two numbers back to binary, 10 and 11. Let's start by the 10. All right. Now, what do you do when you are converting numbers back to binary? You divide them by 2 because binary uses base of 2. All right. So now if you have a 10, let me write it like so. You have the number itself, and then here you have the remainders. Okay. Now you have a 10, and the 10 divided by 2 is going to be 5. Now, did we leave any remainders? No, we don't have any remainders. So here it's going to be 0. Now 5 divided by 2 is going to be 2, 5. You write the whole number, which is 2. What is the remainder? It's 1. Alright. 2 goes 2 times into 5, and then it leaves 1. Then what's 2 divided by 2? It's 1. And do we have any remainders? No, we don't have any remainders. And then what's 1 divided by 2? Well, it's 0 remainder 1. So it's going to just remainder 1. And then here you have your 0. And you can't divide it. When you divide 0 by a number, it's just going to be 0. So this one is just going to be here, and nothing is going to happen to it. Now, when you write the binary representation, you don't write them from the first one going to the right. Going down, all right? Instead, you have to write them from bottom to top. 1, 0, 1, 0. This is the binary representation of 10. Oh, and I forgot the base of 2. Don't forget bases. Alright. That's base of 2, base of 2. And base of 10s, it's not that important to write the base of 10 because it's a natural number. We use this number every day, so yeah, we can't risk that. And then now let's move to 11. Right, we have the number, and then here we have the remainders. This is 11. The 11 that we have. What's 11 divided by 2? Well, I don't know. It's going to be 5. Remainder 1, because 2 goes to 11 5 times, and then it leaves 1 as it is. whatsoever. Now, what's 5 divided by 2? It's going to be 2 comma 5. So it's 2, remainder 1. And then what's 2 divided by 2? It's 1, remainder 0. And what's 1 divided by 2? It's going to go 0 times, remainder 1. Okay, now when you convert again, it's from bottom to up. Now you're going to have the binary representation of 1011. And we did start with 1011 up there, right? Now, for your own practices, convert. Oh, I forgot about the binary. Okay, convert 10101 to a decimal. And back. The second one, convert 110 base of 2 to decimal and back. Right. That's it. Now let's talk about bases. This right here is a base. This right here again is also a base. So the binary representation uses base of 2, right? Let's start with the binary. The binary uses base 2. All right. When you represent a number in binary 10101, you write a base of 2, and we know how this goes. 1 2 3 4 5, so it's going to be 4. Then I omit the 0. Don't omit the zeros when you're writing. All right, I'm just omitting them because of space, right? And then we have the decimal. What do you call it? Yeah, the decimal system. The decimal uses base 10. Right. 379, for argument's sake, base of 10. It's going to be equal to 3 times 10 to the 2 plus 7 times 10 to the 1 plus 9 times 10 to the 0. Then we have the octal representation. The octal uses base of 8. A random number 240 to 64. Base of 8. This is an octal number. If you don't write this base of 8, they're going to take it as if you are writing a decimal. Alright. So be sure to remember this. Now, to convert this to, the conversion or whatsoever that led to this, it was 2 times 8 to the power 2 plus 6 times 8 to the power 1 plus 4 times 8 to the power 0. Alright. Then we have the last one, which is the hexadecimal system. The hexadecimal system uses base of 16. A random number 128 to the base of 16, which is going to be 1 times 16 to the 2 plus 2 times 16 to the 1 plus 8 times 16 to the 0. right? That's that. Now that's going to be that. And then now we have this table. Okay, this table is just binary. I mean, representations of every number in every system, right? In decimal, we have 0 to 16. In binary, still, it's 0 to 16. In octal, we have 0 to 7. And then we have 10 to 20, to 17 actually, then 20, and whatsoever, all right? Now, how I'd like for you to remember this, right, is that the octal numbers are 8, right? From the initial number to the other number to the last number, it's 8. They're going to be 8. How? This is the first number, second, third, fourth, fifth, sixth, seventh, eighth. These are 8 numbers, right? Now from here up to 17, it's still 8 numbers, right? Once you reach 8, you omit 8 and 9. Once you reach number number 8, once you reach uh a sequence of 8, or a sequential value of 8, not a sequential value as in number 8 approximately, but a sequential value of 8, which is 7 in this case. From 0 to 7, it's 8 numbers sequentially. You skip 8 and 9, then you go to 10. You count until 8 numbers, then you skip the 18 and 19, and then you go on. All right, that's how the octal system works. In hexadecimal system, you have 10 numbers. All right, you have 10 numbers that are actual numbers, and then you have 6 more numbers, if not 5, 6 numbers that are what do you call them, letters, right? For example, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and hexadecimal is in 16. So the first 10 is just natural numbers, whole numbers, for yeah, whatsoever. And then the 6 is just alpha numerics. Okay, so here you have your 10, it ends here. And then from here you have 1, 2, 3, 4, 5, 6. Those are your alpha numerics. After 16 comes 17, and 17 will be denoted by 10. 17 base 10. I mean, this is 16 actually. 17 base 16 is just going to be 10. Okay, that's how the number representations work in this case. All right, I hope you caught that. And it's easy drawing this table. You first draw the decimal points or decimal system, then you convert those decimals to binary. Then you convert them to any of these two. You just choose whether you start with hexadecimal or octal. That's on you. All right. And something that is quite important. I don't know if it'll be something that will come up, but you'd be asked to convert octal to decimal. Now, to convert octal to decimal, you first convert this octal to binary, and then you convert this binary to hexadecimal. But let's not do that. All right, let's not do that. It may be something that you want to do at your own time. All right, if you have that much time in your hands, you can do that. All right. Now, I did speak about conversions. Let's just get into them in depth. Conversions. All right. Now, I've already showed you how to convert binary to decimal and decimal back to binary. So now here I'm going to do binary to octal and whatsoever, then binary to hexadecimal, and then that's going to be it, right? Now the binary to octal, let's see, these numbers are hard to have. One base of 2. This is binary. Let's convert this number to octal. All right. Now When you convert to octal, you are going to group the binary digits in groups of 3. You group the binary digits in threes from right to left. Okay, now let's see. The first number that we have is 001. That's 3. Then we have 011. And then we have 01. But we need 3 values. So at the front we add a 0. Now this 0 is the it doesn't have any changes actually, right? This 0 right here doesn't have any changes. Unless if we were to put a 1, we were going to get a change. It's like if I'm sending you 100 rands, and then I just mistakenly click a 100, you're still going to get this value and this one, just that it won't show up, right? So that's the binary representation. That's going to be the trees. Okay, now let's convert this number right here. What's going to be this number? Oh, it's going to be 4, because 1, 2, 4. 4 is the only one that's on. All right. Now let's move to this one. We already have a 4, and then here we have a 2, so this is going to be a 6. Then the last part, we have this one. We have a 2. So this is going to be 246. All right. Now the binary representation the octal representation of this binary number is this 246. So you end up saying 101. The first 0 wasn't there actually. So 110,100 base of 2 is equal to 264 with the base of 8. Okay, that's how you convert binary to octal. Now let's convert octal to binary. 440 octal to binary. Let's say we have 440 in octal, and we need to convert it back to binary. Now, we do know when we convert things to binary, we just say those numbers 0, 4, and 4. Then we convert them back. We know that this is just 3 zeros, 1, 2, 3. And then we know that this is just 100. And then we know that 100. And then this is also 100. So our binary representation is going to be 100, 100, 0, 0, 0. This is our binary representation of the octal number 440. Now let's convert binary numbers to hexadecimal numbers. The hexadecimal numbers are so long. 2 hexadecimal numbers. Okay. Now I got this number from last year's test. I did send the question papers. Yeah. Blah, blah, blah. Okay, now let's convert this following number. 111 0 0 0 0 1 1 1 0 1 1 0 1 1 0 0 1. Base of 2. Did I write the base here? Oh yeah, I did write the base. Okay, now let's convert this number to hexadecimal. Now, when you convert binary to hexadecimal, you're going to group. I can't spell. You're going to group the binary digits in 4s from right to left. Right. Now let's group these numbers. We have 1, we have 2, we have 3. Let's see, 4. Oh, we have 4, and then we have 5. We just add a 0 right here. Right. Now let's start from the further right. We have 1001. What's this number in hexadecimal? It's 9. And I think 9 in hexadecimal is 9, right? 8 and 9. Hexadecimal, yes, it's 9. Okay, now we have this number right here, 1101. We have 8, 12, 15. And what's 15? It's F. Then we have this other number, 1110. Let's see, 8, 10, 14. 14 we have E, EF. Yes, we have E. And then here we have whatsoever. That number is 0. Then what do we have here? 4, 6, 7. Then this is going to be our hexadecimal representation. So 7, 0, E, F, 9, base of 16 is going to be our hexadecimal representation of this big binary number that we have up there. All right. So that's that. All right. Now let's convert a hexadecimal number to a binary number. All right. Now we have this number 960b. Right. Let's just do this. 0, 6, then 9. Okay, now let's start from B. Okay, so from B, at B, we know that this is going to be, let's see, 10, 11, 12. B is 12. B is 12, but according to the table, it's 11, if I'm not mistaken. B is 12, but according to the table, it's 11 right there. I'm not mistaken. So how do you denote 12 in a binary system? Okay, let's just have all ones up. Okay, now to have 12, you need this number right here. You need an 8, and you're going to need a 4, and you're going to need a 2. So, well, actually, you're not going to need a 2, so it's just going to be 1, 1, 0, right? 1, 1, 0, 0. This is going to be our B. We only need 8 and 4 to have a 12. Then let's go to a 0. We know that a 0 is just 0 all over. And then let's go to 6. We have 4 ones. Now, which ones do we need? We need a 4 and a 2. So it's going to be 0, 1, 1, 0. And then let's go to 9. 1, 1, 1, 1. Which numbers do we need to have a 9? We need the first one and the last one. So it's going to be 1, 0, 0, 1. All right. This is going to be the binary representation of that number. So 1, 0, 0, 1, 0, 1, 1, 0. I should write this next to each other actually. Then 0, 0, 0, 0, 1, 1, 0, 0. This is going to be the binary representation of the hexadecimal number 960b. Alright, don't forget the bases again. Okay. Now let's go to the fractional point of fractional notation. Now we have this number 101, 101. Alright. Now how would you convert this number to a decimal number? Well, we do know how to convert these numbers right here. Right, we do know how to convert these numbers right here. It's going to be a 5, if I'm not mistaken. And then when we convert these ones, when going to the right, after the radix point, and you convert going to the right, and you don't start by 1 or over 0. No, you don't start by that. So when you start converting, you start from a 1. So you say 2 to the negative 1, and then you go again to the right, which is 2 to the negative 2, and then you go to the right, which is 2 to the negative 4, in which these values are just 1 over 2 plus 1 over 4 plus 1 over 8, and so on. Right? That's just the representation. Okay, but I'd advise you to use these ones because they are like a standard of using. Now let's convert this number right here. Okay, we have 1, 0, and 1. So what's this 1, 0, and 1? Well, from this side, the 1, 0, and 1 is just 4 plus 1, which is going to be 5. Right here. And then this 1, 0, 1 right here is going to be 1 times a half plus 0 times 1 over 4 plus 1 times 1 over 8. Now let's see, 1 over 2 plus 1 over 8 is going to be 16. 8 plus 2, which is 10. Then it's going to be 5 over 16. 10 over 16. Then divide by 2. It's going to be 5 over 8. So this is going to be 5 and 5 over 8. Right, this is how you convert these numbers. It's going to be 5 and 5 over 8. That's it on the fractional part. Okay, now let's talk about the excess notation. Now in excess notation, we have an excess of 4 notation, 4 notation, or 4 excess notation, in which it's just 3 bits. Right, what is 3 bits? 1, 2, 3. 1, 2, 4. This is 4 notation. Right. This is 4 notation. 3 bits is 4 notation. Then we have 8 notation. 4 bits is 8 notation, yes. Which is 4 bits. 1, 2, 3, 4 bits, which is 1, 2, 4, 8 notation, right? Then you have a 16-bit notation, but I won't talk about that anyways. Then you have a 128 notation. At a 128 notation, I think it's 8 bits, right? 1, 2, 3, 4, 5, 6, 7, 8. 0, 2, 4, 8, 16, 32, 64, 128, yes. Which is going to be 8 bits. Okay. 128 notation is an 8-bit notation. Okay. Now let's go to the floating point. Now in the floating point, we're going to use the 8-bit notation, or the 128 excess. We're going to use 8 bits. And then from chapter 1, if you do remember, we had the high order and the low order ends, right? Now here we have a high order bit and it's a sign. Now this can either be a 0, which is positive, or a 1, which is a negative. Right. That. Now in this 8-bit notation, we have like 8 bits, right? And when you are converting a number to a floating point notation, I don't have any numbers in head, but I'll just try to imagine something. Okay. Now, when you're converting a number to a floating point, you take the high order bit first. Okay, you take the first number that you come across. You count from uh, left to right. In this case, instead of right to left, you count from left to right. You're going to take the first number and then you put it in the sign table. Okay. Now this is going to be your sign. All right. And then in that 8 bits, you are left with 7 bits. 2, 3, 4, 5, 6, 7. All right. Now you have these 7 bits. All right. And now in 8-point notation, we use 3 bits for our exponent. Okay. So we take 3 bits and then we say this is our exponent. And then the last 4 bits are our mantissa. All right. So you take the sign and then in the left 7 groups, you divide them into 2 groups, the exponent and the mantissa. Now let's convert a number. We have 0, 1, 1, 0. Right, then we have 1, 0, 1, 1. Okay, now when we convert this, we first look at this part. This is a sign bit, which is a positive because it's 0. Alright, then we have the exponent and then we have the mantissa. And how do we convert this? We extract the mantissa. Well, before we extract the mantissa, let's find out how much this exponent is. Alright, now according to the 3-bit table, the 3-bit table, we have 1, 0, 0, which is a 0. This is our starting point. And then going down, we have 0, 1, 1, which is a -1. Then we have 0, 1, 0, which is a -2, negative. Then we have 0, 0, 1, which is a -3. And then we have 0, 0, 0, which is a -4. Right. Now, when we go up, we have 1, 0, 1, which is equal to 1. We have 1, 1, 0, which is going to be equal to 2. And then we have 1, 1, 1, which is going to be equal to 3. Right. This is our 3-point notation. 3-bit notation. Now, we come and check this number. Alright, it's 110. What's 110 in our 3-bit? It's 2. So it's going to be 2. Right? Our exponent is going to be 2. Now we extract our mantissa with a radix point. We put a radix point and then we extract our mantissa. Oh, it's 1, 1. Alright, and then we look at the exponent. The exponent is positive. So we're going to move our mantissa 2 points to the right. If it was negative, we're going to move our mantissa 2 points to the left. Alright. So now here we have our 1, 0, 1, 1. And then we move our our radix point 2 points to the right. Right. It's going to be 1, 0, 1, 1. Right. Now what is 1, 0, 1, 1 in decimal points? This is 2 because it's 1, 2. Then this is 3/4. How is it 3/4? 1/2 plus 1/4, which is going to be equal to 8. Then it's 4 plus 2, which is 6. Then divide by 2, this is just going to be 3/4. Right. So this is going to be 2 and 3/4. So 10,11 it's equal to this decimal number. All right. Now when you end your question, because they say extract it, or convert it, you end up saying that this number base of 2, I forgot, this number as a whole. Let's see if I can get it out of here. Now you end up saying that that number is equal to 2 and 3/4. All right, this is how it is. And then now let's talk about converting, or I mean encoding. All right, converting a number, a decimal number, to the floating point. All right. Well, you're encoding from floating to binary. All right. So let's say we have a number encoding. Let's say you have a number, a -9/16, right? Now, first of all, we are going to convert this number into a binary number. Already you have a negative right there. You don't have an exponent or whatsoever, so that's going to be a 0. And what else? Okay, that's it. Now we are going to find a number that is equal to 19/16. In our floating point, or in our mantissa, we don't have any number that gives us 9/16. So let's try to multiply this number by 2. All right. Now multiplied by 2, this number is going to be 18/32. Now I can think of two numbers that can give me an 18 in the top and a 32 at the bottom, in which it's 1/2 plus 1/16. Why? 16 plus 2 is 18, right? And then 16 times 2 is going to be 32. And this is going to be equal to 9/16. So we are going to have these two numbers. All right. These are our two numbers that are on. Now let's convert these numbers. Let's just take 5 for argument's sake. It's 2, 4, 6, 8. 2, 4, 8, 16. So we have our 1, 0, 0, 1 as our what do you call this? As our 9/16. All right. Then our radix point is going to be here. Okay. And at this part we have a 0, obviously. Now what are we going to do? Let's see. Well, there's nothing that we're going to do because it's 0. We can't actually move our radix point anywhere. All right. So our radix point is going to stay here. So this is going to be our mantissa. All right. Our mantissa is 1, 0, 0, 1. Then our exponent is 0. And from the 3-bit axis, or the 3-bit notation, we know that a 0 is denoted by a 100, right? 100. And our sign is negative. So at the front, we're going to have a 1. So now this thing right here is equal to a -9/16. Okay. This is how much we get from yeah, but this is what we get. This is the binary number. This is the binary representation of this decimal number right here. Okay, now let's talk about lost bits. Okay, let's take this number again, like as it is, this number as it is. Yeah, let's say we have a negative 9/16. Now we do know that a 1 is denoted by, it's a 1 actually. A 1 in binary and in decimal is the same. We already have our mantissa point, or our whatsoever point right here. Right, we have our 1, 0, 0, 1. And then here we're going to have our radix point, and then we have a 1. Okay. Now because this one is negative, we're going to take this radix point and move it 1 point to the left. Okay. Now it's going to be 1, 1, 0, 0, 1. Now this is going to be our mantissa, but when we write down our mantissa in the mantissa field, we write them from left to right. All right, so this one is going to be a lost bit. That's called a truncation error or whatsoever, rounding error. So our mantissa now is going to be 1100, and we know that a -1 is denoted by what's that again? 0 1 1. Then this is going to be 1. This is going to be possibly our representation of -1 with the 9/16. All right, now let's move to this thing. What is it called again? Ones complement. Yes, it's called the ones complement. Okay, now in ones complement, it may happen that they give you two binary numbers which you have to subtract, or whatsoever that is. Okay, it may happen that they give you two binary numbers so that you can subtract one from the other. Let's say maybe they say you subtract this number right here from, let's say they say subtract this number right here from the one that's above, right? For argument's sake, I'm just going to pick like random numbers. Okay, we have 1 0 0 1 0 1, and then down here we have, oh no, let's say we have a 0. Let's see, 1 2 3 4 5 6 7 8 1 1. All right, and then down here we have 1 0 1 1 0 1 0 1. All right, this is a number that you're subtracting from this one. All right, this is the menu whatsoever, and then this is the subtrahend. I can't spell, but you get what I'm saying. Then the first thing that you're going to do, you're going to convert this number into the complement. All right, a complement is when you take numbers, or it's when you convert numbers to be the exact opposite. All right, now the subtrahend 1 0 1 1 0 1 0 1 binary. I forgot that it's binary. It's going to be 0 1 0 0 1. Wait, 0 0 1 0 1 0. This is going to be the complement of this subtrahend number. Right, now we take the first number. 0 0 1 0. All right, and then we add it to the subtrahend. Okay, we're going to add the number to the subtrahend, which is 0 1 0 1. Oh, why is it like I copied the same number? Yeah, I think I copied the same number, but anyways, let's go on. 1 0 0 0 1 0. I think I copied the same number, but that's fine. Then we're going to add these numbers. What's these two? What do these two numbers give us? They give us a 2, and the 2 is denoted by a 0. I mean a 1 0. So we write the last 0, and then we carry the 1. All right. Now we add these two, this one and this one. They're going to give us a 0. I mean a 1 0. So we carry the 1, and then we add the 1. We're going to get a 1. Then here we have 0 plus 0, which is 0, plus 1, which is 1. Then here we have a 1 and 1, which is going to give us a 2, and is denoted by 0 1. So we take the 0, carry the 1, still the same, then 0, then this is 0, and then this is 1. Right, and then here we don't have any carry. Okay, so this is going to be the number that we get from subtracting two numbers and whatsoever. All right. Now let's say, for argument's sake, this number right here, where is it? This number right here is a 1. Right. Let's change that number to a 1. It won't affect anything in this equation. Right. Now, because we had a 1 and 1, which is a 2, and then 2 is denoted by 0, 1, then we carry a 1 right here. Right. And here, we are going to say 0 plus 1, which is 1, plus this one, it's going to be 2. So we're going to write our 0 right here, and then we carry a 1, in which our 1 is a carry. Alright. Now, because we have a carry of 1, we're going to take this 1, and then we add it to the number that we got in the previous answer. Okay. So we're going to take this one, and then we say we're going to add it right here. Alright. Now, the final answer is just going to be 1, 1, 1, 0, 1, 0, 0, 0. Right. This is going to be the subtracted, the answer in 1's complement. Alright. And that's it. Now, let's move to the 2's complement. Okay, now in the 2's complement, it's usually used by, or mostly used by, our computers. Alright. Now, the 2's complement involves taking a binary number. It involves taking the subtrahend and converting it. I don't know the word that I can use instead of converting. Alright. It's like converting those ones to zeros and zeros to ones. You're just complementing the binary number. Alright. And converting it to the complement, then add 1 to that complement before subtracting from the minued value. Alright. So you take the subtrahend and convert it to its complement, and then you add 1 to that complement before you subtract it from the minued. Right. For example, now this thing, alright, it works when subtracting. Whenever you have a negative number, you use the complement and then you add the 1. Right. Let's say, for example, we're adding numbers. Let's say 8 plus 2, and we're going to be using 8 bits. Okay, 8 plus 2 is equal to 10. Right. Now let's use 8 bits, the 8-bit notation. Okay, so our 8 is going to be 1, 0, 0, 0. That's 4, 5, 6, 7, 8. Then our 2 is just 1, 0. Then 3, 4, 5, 6, 7, 8. Alright. Now when you add these values, it's going to be 0 and 0, 0, 0 and 1, it's 1, 0, 1, 1, 2, 3, 4. This is 10 in binary, right? 10 is equal to this in binary, right? Now let's say we want to subtract. Alright, let's say 8 minus 2, in which it's going to be 6. Right, we already have the binary number for 8, which is 0, 0, 0, 0, 0. Oh no, 0, 0, 0, 4 zeros actually. Then 1 and 3 zeros. Oh, binary. Okay, and then we have a plus 2 right here, and then we take a plus 2's complement. Let's complement that number before we add it. All right, we're going to say 1, 1, 1, or maybe let me start from the further right. We're going to say 1 0 1 1 1 1 1 1 1. All right, and that rule said that this thing right here, it said that you add 1 to that complement, right, before you subtract from the menued thing. Okay, so this one we're going to say plus 1. Okay, and then this plus 1, let's see, it's going to be 0 carry, then it's going to be 1, then it's 1 1 1 1 1 1 1, right? So now we're going to take this value right here, okay, and use it to add it to this number right here. Now let's add these numbers. Here we have a 0. Here we have what's this? A 1. Here we have a 1. Here we have a 0. Carry the 1. So that I don't get confused, let me just this one and this one, this one and this one, this one and this one, this one and this one. Now here we're going to have a 0. Then we carry a 1. Then we're going to have a 0. 1 2 3 4 5 6 7 8 9. Oh, okay, no wonder this last one is not here. No wonder these numbers appeared larger. Okay, now we have 0, carry the 1. We have a 0 again, carry the 1. We have a 0 again. Now we have a 1 that's left. And then we just, because it's 2 complements, we just let that 1 disappear, right? Now in binary representation, this is our 6, right? Because we have a carry in 2's complements, when we have a carry, we just let it disappear. We don't care what happens after you have the carry or not. We just let it go. Okay, let's see, 1 2 3 4 5 6 7. Okay, it's going to be a 0. I forgot. And this is pretty much it. Okay, now let's do the last example where it's 2 negative numbers. All right, let's say we have a negative 6 minus and a negative 8 actually. All right, now let's convert these numbers into binary. Now, no, we convert their positive values. All right, we convert the positive values to binary, and then we find the complement. The complement is the negative. Okay, now let's find the binary representation of 6. Right, we don't need a 1, the foremost one, but we need these 2 2 and 4 to have our 1. Then that's it. Then we add the other 4 zeros. 1 2 3 4 5 6 7 8. Okay, this is going to be our binary representation of 6. Now let's convert it to a subtrahend, or to the complement. It's going to be 1 1 1 1 1 0 0 1 plus 1, which is going to be 0 1 0 1 1 1 1 1, right? 1 2 3 4 5 6 7 8. Yes, and then we go to a negative 8. We check the binary number for 8. We don't need this one, we don't need this one, we don't need this one, but we need this one. Then we add the other 4 zeros. 4. Then we convert this to the complement, which is going to be 1 1 1 1 0 1 1 1. Then we add a 1, sorry. Then we add a 1. Here we are going to have a 0. Then we have a 1 right here, we're going to have a 0. We have a 1 right there, we're going to have a 0. We have a 1 right there, we're going to have a 1 1 1 1 1. Now this is going to be our negative 8. Okay. Now when we add these two, we take the first one. We have 1 1 1 1 1 0 1 0. Well, this is actually equal to negative 14. Okay. Then we take this one again in binary. Then we have 1 1 1 1 1 0 0 0 in binary. Then now we add these numbers. Here we're going to have a 0, a 1, a 0, a 0, 0, 0, 0, 0, and then the 1 is discarded. All right. This is going to be our negative 14. Surprisingly so. All right. This is how it works. All right. So I did binary additions as well as decimal additions at the same time. All right. Now you can try out the additions of hexadecimals and the additions of octal numbers. All right. And don't forget that you have to use that table. You can draw it down, but you shouldn't be referring to the actual table. All right, from 0 up to 16. Okay, now let's go to data compression. Now in data compression, we have two categories of categories of compression. Now the first one is the lossless. Now the lossless doesn't lose information during compression. And then we also have the lossy, which is just the opposite of this one, which loses information during compression. This isn't during compression, it's during the compression process. Yes, during the compression process, right? It doesn't lose information during the compression process, and this one loses information during the compression process. All right. In which number one we have the run length encoding. Now in the run length encoding, this just produces or produces its best result when the data is being compressed. That's the run length encoding. After the run length encoding, we have the, let's see, RRF. Oh, all right. We have the relative encoding. And the relative encoding just records the difference between consecutive data blocks rather than the entire block. And then the last one, RRF, we have the frequency dependent encoding. All right. Now this one, how can I explain this one? It's the length of the bit pattern used to represent the beat, and then that is inversely related to the frequency of the items used. So the length of the bit patterns is used to represent the bit items is inversely related to the frequency of the items used. All right. This is the frequency dependent encoding. It takes frequency rather than the whole thing, right? Now, the last encoding technique is called the come on, what's going on now? Okay. The Limpel. Sorry, I'm just tired. It's called the Limpel Ziv technique, which was made by Limpel Jacob, I think. I don't know. And this one uses the LZ77 system, which represents the rest of the message as a sequence of triples. And these triples, come on, And these triples that we're talking about consist of a number, well, two numbers in which they are integers, two int followed by the symbol from the message. Okay, let's say for example we have A, B, C, B, A, C, D. All right, and then here we have a 5, a 3, and F. All right, this. Now this first number states that move from the last letter, exactly the last letter, move 5 points to the left, or 5 characters to the left, in which is going to be 1, 2, 3, 4, 5. And then this one says copy the 3 letters to the right from where your 5 ended. Right. So the 5 ended here. Now we're going to copy 1, 2, 3. So we're copying C, B, A. All right. So we're going to copy this whole message. Then we add CBA. And then we add F. So it's going to be A, B, C, B, A, C, D, C, B, A, F. This is going to be our Limpel-Ziv encoded message or decoded message. All right. Now there's another one in which we're not going to use it. It's called the Limpel Ziv Welsh. The LZW. Right. We're not going to use this one, but I'm just going to give you an insight of what it's about. Or maybe let me just go with that. Okay, here it is. All right. The Limpel Ziv Welsh. Oh, all right. And this one doesn't work the same as the Limpel Ziv. This one works in a different way, in which I can't actually explain it in a way that you'd understand. But if you go to your prescribed book and go to page 97, you're going to find this thing. Oh, sorry, 94. If you go to page 94, you're going to find these things right here. Okay, so now let's move on to the last section, which is called the parity bits. All right. Now, in the parity bits, in short, you need to have in your binary system or binary numbers, you need to have an odd number of ones. Every time when you get a binary system, you need to have an odd number of ones in this specific case. All right. Now, if the numbers are even, you're going to then add a 1 at the beginning. All right. And if number of ones is odd, add a 0 at the beginning. All right. Now, let's say, for example, we have a D. All right. Now, how is a D? In ASCII, in the ASCII table. Okay, in the ASCII table, we have a letter D. This is how it's represented. It's in 0, 1. Then what goes after 0, 0, 0, 1, 0, 0? It's supposed to be 8. 1, 2, 3, 4, 5, 6, 7, 8. Then where did I go wrong? All right, I see. It's supposed to be 1. Yeah, this is going to be the ASCII of D. All right. This is how the D is represented. Now, when you add a parity bit, you first check this thing. Does it have an odd number of ones? No. So we are going to copy it as it is. Okay. And when you copy it, the first number right here that you're going to put in it's called the parity bit. You're going to put a 1 right here. Now this is going to be your new binary representation. Okay. Now let's move to another letter. Which letter can I go to? Now the R in the ASCII, I think it's 0 1 0 1 0 0 1 0. So this is going to be your R in ASCII. I mean, yes, in ASCII this is your R, and then you count the number of ones. Do we have an odd number of ones? Yes. Then right here you're going to add a 0. All right. Then it's going to be like that. And then the new binary representation of this one is going to be like this. All right. This is how it is. Now let's move to the last part. This is the last part. The last part. The hemming process. The hemming thingy. I don't know, but it's hemming anyways. Okay. So let's just say maybe you're asked to find the hemming distance between C and D. All right. Now let's count the hemming distance. D doesn't have a 1 here. Oh, come on. D doesn't have a 1 here. So it's going to be 1. D also again doesn't have a 1 here, so it's going to be plus 1. Then it doesn't have a 0, then it's going to be plus 1. Doesn't have a 0, then it's going to be plus 1. It does have these two, so it's going to be 1 plus 1 plus 1 plus 1, which is going to be 4. So now the hammering distance for this, the hammering distance is going to be 4. All right. This one is easy. The parity bits, the hammering distance, and the limp ziv. I think these ones you can get them